Hello and welcome to my channel. Today I'll be discussing, can the four forces explain everything in the universe? What is the mysterious fifth element? If you're ready, let's dive into the best video explaining this topic.
You experience how strongly the earth pulls you down every single day. If you were to jump right now, you'd snap right back down to the ground. Likewise, a paperclip also falls straight to the ground in the same way. But this tiny little 1 centimeter magnet easily lifts the paperclip, overcoming the gravity of the massive Earth, 12,756 kilometers in diameter, that pins everything from vast oceans to tiny leaves to the ground. How is this possible? And as I mentioned to you before, if in reality we can never actually touch any object, then what is it that we feel at our fingertips when we come into contact with things? Seriously, how is it that we can explain everything? Absolutely everything, from black holes to a refrigerator, from the interaction of a wheel with the road to the tides that can move entire oceans, from atomic bombs that can vaporize hundreds of thousands of people in milliseconds, to all the electrical activity in our brains with just four and only four forces: gravity, electromagnetism, the strong force, and the weak force. Or can we really? Because we can't explain problems like dark matter, dark energy, and the matter-antimatter asymmetry with the physics we currently have. Could it be that we need to discover a fifth force to solve these issues? So today, let's sit down together and take a closer look at these strange things we call forces. We have a project. The link you need is pinned in the comments. Now, let's start with the word kuvvet, force strength. This word, which means power in Arabic, is thought to have entered Turkish before the 1300s. Interestingly, around the same time, the old French word fortis, which has the same meaning, entered English as force. However, the first use of this word in its scientific sense is found in Aristotle. Aristotle wrote that all objects want to remain at rest and that a constant force is needed to keep them moving. Today, thanks to Galileo, we know that Aristotle was wrong. Moving objects are not inclined to stop, as Aristotle thought. On the contrary, all objects tend to maintain their current state of motion without change. In other words, as you might remember from high school physics, objects at rest tend to stay at rest, and objects in motion tend to stay in motion. The first person to give a concrete and mathematical definition of this fundamental physical law was Isaac Newton. Although Newton himself did not write it in this form, in his famous formula summarized as F equals m times a, he proposed that what we call force is the product of mass and acceleration, that is, the change in velocity. And you can also understand this intuitively. The greater the mass of an object, the more force is required to change its speed. Similarly, the more you want to change an object's speed, the more force you need to apply. Newton was the one who formulated this fact. What makes this formula powerful and has allowed us to explain countless observations for centuries is that it is incredibly general. In other words, it can explain a large portion of the interactions we see around us all by itself and in an extremely simple way. When combined with other relevant formulas, F equals ma can successfully explain not only the motion of planets around each other, but also deceleration due to frictional force, creep under tension, the normal, i.e., perpendicular forces that objects exert on the ground, forces generated during collisions, air resistance, and even the movements of objects changing direction under electromagnetic forces. Before Newton, this was impossible. Newton literally gave us a Swiss Army knife. But when you think of force, don't just think of interactions between objects that are in contact. Because, except for a couple of extremely rare cases in nature, there is no such thing as contact at the atomic scale. For example, when you press your hand against the table, the resistance you feel in your hand is actually a complete illusion. At the atomic scale, the atoms in your hand never actually touch the atoms in the table. There is always a gap in between. But because the atoms in our hand are repelled back with different forces depending on the hardness, roughness, and material of the surface, we feel as if there is contact between them. That's why it's much more accurate to think of forces as interactions. In fact, to bring it even closer to everyday life, you can even think of forces as a form of communication. For example, when you call a friend who is far away to make plans and do something together, you are actually behaving like fundamental particles. You are far apart, but a message is being sent from one of you to the other. And this communication, in the case of the phone example, happens through what we call radio waves, photons that are invisible, low energy, and have a long wavelength. In other words, via electromagnetic interaction. Depending on the information carried by that interaction, certain changes occur in your friend's brain, and they decide whether or not to meet up with you. If you recall the famous chart I showed in the video about the God particle, the objects that communicate, like you, a star, or any other matter, as well as their counterparts, antimatter, are made up of the quarks and leptons on the left side of this chart. But today, our topic isn't them. It's the bosons on the right side of the chart. In other words, force or interaction carriers. And remember, the Higgs boson, which is mistakenly called the God particle and gives other particles their mass, is, as its name suggests, also a boson. But unlike the other bosons, it is not a vector boson. That is, it doesn't have both a direction and a magnitude at the same time. The Higgs is a scalar boson, meaning it has a certain magnitude at every point in the universe, but no direction. Let's set that aside for now and start with gluons. Gluons, as we discussed in the video, why doesn't the atom spontaneously fall apart, are the carriers of the strongest force in the universe, the strong force. This force determines how the quarks that make up the protons and neutrons inside the atom interact with each other. So we don't really feel this force in our daily lives, but we can see its effects everywhere, all the time. Because if the strong force didn't exist, atoms couldn't stay together and would fall apart. And you can understand the strength of the strong force from this. At least in the low energy regime, this force is 137 times stronger than electromagnetism, which is the second strongest force, 1,000,000 times stronger than the weak force, which is another nuclear force we'll discuss in a moment, and about 100 trillion times stronger than gravity, which you're most familiar with. Yes, I'm serious. And this ranking automatically answers one of the questions we asked at the beginning. A magnet can easily overcome the gravity of the entire Earth. Because, per interaction, electromagnetism isn't just a few times stronger than gravity, it's trillions upon trillions upon trillions of times stronger. Anyway, thanks to the strong force carried by gluons, which get their name from the word glue, meaning sticky, quarks are held together so tightly that it's almost impossible to separate them from each other. And that's not all. Because gluons interact not only with the particles they mediate, but also with each other. When you try to pull two quarks apart, the strong interaction between them doesn't weaken with distance as it does with other forces. On the contrary, just like a stretched spring, it actually gets stronger. And as you may recall from the quantum chromodynamics theory we discussed in the Higgs video, every quark has a property called color charge. And because this charge must always remain neutral, quarks can never exist on their own. They can only exist together with one or two other quarks to neutralize their color charges. Because of this strange dynamic, if you try to separate two quarks too far from each other, the interaction between them becomes so energetic at a certain point that just as they are about to break apart and exist on their own, a new pair of quarks spontaneously appears out of nowhere, matching the energy of the strong interaction between them. And these newly created quarks pair up with the ones you tried to leave alone, ensuring that they remain color neutral. The quantum world is truly bizarre. Anyway, in summary, the strong force is a very important part of atomic stability in the universe. Because without it, the positively charged protons in the nucleus would repel each other, and the atomic nucleus would spontaneously fall apart. But the strong interaction overcomes this repulsion and holds the nucleus together. Therefore, the internal structure of the atom, the nuclear reactions in stars, and even the existence of our own bodies all depend on this interaction. Alas, it's not enough for everything to just stay together. For the continuity of the universe, sometimes things need to change as well. And in a very interesting way, there is a force in nature that can transform one particle into another. For example, turning a proton into a neutron or a neutron into a proton. A force that appears everywhere in nature, from the radiation of stars to nuclear radiation. The weak interaction or the weak nuclear force. The name of this force comes from the fact that, just like the strong nuclear force, it is mostly observed in nuclear processes, but sometimes also in non-nuclear situations such as neutrino interactions. But as you can tell from its name, it is much weaker than the strong nuclear force. The reason for this weakness is that, compared to the other force carriers, the bosons that mediate the weak interaction have extremely high mass. By the way, when we describe bosons as force carriers like this, we tend to think that just as a rope carrying a weight in everyday life is usually lighter than the weight itself, bosons should also be lighter than the particles they act between. And in most cases, this is actually true. But if we go back to our table, we see that the three particles that are the carriers of the weak interaction, namely the W+, W-, and Z0 bosons, not only outweigh the electron, but even have a greater mass than a proton. It is precisely because of these enormous masses that the range of this force is much shorter. And as you can tell from their names, the W+ is positive, the W- is negative, and the Z0 is a neutral boson. The reason we talk about charges in these bosons is that in the weak interaction, a particle's type can change while its charge can also change at the same time. For example, while neutrons can remain stable together with protons inside an atom, if you leave a neutron on its own, it decays into a proton in just 15 minutes. It is the weak interaction that enables this transformation. And in this example, since a neutral structure turns into a positive one, the interaction here is mediated by the W- boson. In cases where a proton transforms into a neutron, the W+ boson comes into play. So these bosons are not just mediators, they also determine the direction of the transformation within the framework of the law of conservation of charge. Here's a critical point. The only force that can transform one particle into another is the weak interaction. So, the strong interaction holds quarks together. The electromagnetic interaction, which we'll see in a moment, brings charges closer or pushes them apart, and gravity keeps planets in orbit. But only the weak interaction can transform one particle into another. So, at the core of the formation of elements in the universe, the aging of atoms, and the energy production of stars lies this transformative force. At this point, we can move on to the electromagnetic force. Because when we add the photon, which is the carrier of the electromagnetic interaction, to the W+, W-, and Z0 bosons, we obtain a unified force that can be explained by a single theory called the electroweak interaction. Just like how electricity and magnetism were once thought to be separate forces, but later it was understood that they are different manifestations of the same force. Similarly, at a certain point in the history of the universe, the electromagnetic force and the weak interaction were exactly the same force. But due to the incredibly rapid cooling that occurred just a very short time after the Big Bang, these two interactions also separated from each other and turned into different forces. So it seems that some forces can be derived from others. Let's keep this in mind for now. It will come up again shortly. When people hear electromagnetism, they usually think of electricity, magnets, and if they're a bit familiar with the subject, maybe light as well. Because remember from the video, why is the speed of light 300,000 kilometers per second? The only reason light, that is, photons, has a constant and unsurpassable speed is the interaction between the permeability of the universe's electric and magnetic fields. Therefore, the reason light exists at all is electromagnetism. But the electromagnetic force is actually much more than that. In fact, electromagnetism is one of the most comprehensive and limitless interactions in the universe. From the interaction that occurs between your finger and an object when you think you're touching something, to the movement of electrons around the atom, from almost all of chemistry to light, frictional forces, and even the very fact that you can watch this video, electromagnetism alone is responsible for most of the interactions you can and cannot imagine. Of course, we also encounter electromagnetic interactions on much larger scales in everyday life. The electric current that powers our computers, cell phones, airplanes, cars, hair dryers, medical imaging devices, and all our other electronic devices is essentially nothing more than the collective movement of free electrons within conductive materials and the electromagnetic interaction that occurs between wires and the universe. We discussed the details of this in the video about lies related to electricity. In other words, this interaction in nature both forms atoms on a microscopic scale and brings our technology to life on a macroscopic scale. But perhaps the most important effect of the electromagnetic force on the universe is seen inside atoms. You must have thought about it at some point. The negatively charged electrons orbiting the positively charged atomic nucleus due to the protons are constantly being pulled toward the nucleus by the electromagnetic force. But what prevents the electrons from crashing into the atomic nucleus is, as we saw in the ultraviolet catastrophe video, the fact that quantum mechanics operates in a quantized, that is, discrete nature. We always think of electrons orbiting the atom as if they were satellites orbiting planets. But this is completely wrong. A satellite orbiting a planet can eventually crash into the planet it orbits, as it continuously loses its energy. For example, Mars's moon Phobos gets 1.8 meters closer to Mars every 100 years, and in about 50 million years, it will be torn apart. But electrons cannot lose their energy in such a continuous way. They can only lose or gain energy in discrete steps like the rungs of a ladder, and electrons are already at the lowest energy level possible around the atomic nucleus. That's why even the single electron around hydrogen cannot be pulled into the nucleus by the proton. Because quantum mechanically, there is no lower energy level for that electron to drop to. But if the electromagnetic force didn't exist at all, there would be no force left to localize electrons around the atomic nucleus. Therefore, atoms and electrons wouldn't interact, all electrons would be free, chemistry would come to a complete halt, and the universe as we know it would largely come to an end. That's why the dance between the electromagnetic force and quantum mechanics is extremely important. It might surprise you that the carrier particle of the electromagnetic interaction is not a charged particle like the electron, but rather an unrelated and neutral particle like the photon. But it shouldn't, because when two electrons enter each other's electromagnetic field, the things that enable the interaction between them are photons, which essentially act as a bridge between the two electrons. More precisely, virtual photons. The reason these are called virtual photons, or more generally, virtual particles, is that at such short distances, these interactions occur in unimaginably brief moments. And although we can observe the bosons responsible for these interactions with our own eyes in high-energy hadron collider experiments, for the most part they are essentially mathematical constructs. In other words, virtual photons are not like ordinary photons that carry light, but they still behave like photons. For example, as I mentioned, unlike W and Z bosons, these are massless and chargeless. That's why they cannot interact with each other. And more importantly, it is precisely for this reason that the electromagnetic interaction can have an infinite range. So, although the electromagnetic force does weaken significantly with distance in practice, in theory, it never actually reaches zero and can extend from one end of the universe to the other. However, another critical importance of electromagnetism being carried by photons is this. Since photons do not travel at infinite speed, all electromagnetic interactions always propagate at the speed of light, which is 300,000 kilometers per second. In other words, for one electron to sense another electron or a proton, it first needs to exchange a photon with it. And as a result of this exchange, depending on the electric charge they communicate to each other, they either repel or attract one another. And this was actually one of Newton's greatest mistakes. According to his model, if the sun were to suddenly disappear with a poof right now, we would see it instantly, and the Earth would immediately leave its orbit. However, the photons emitted just a fraction of a second before the sun disappeared would take 8 minutes and 20 seconds to reach the Earth due to the 150 million kilometers in between. Therefore, we wouldn't realize that the sun had disappeared for about 8.5 minutes. But what if the sun disappeared? Would we immediately leave our orbit? Well, this brings us to the force that made Newton famous, gravity, which is the weakest among the four fundamental interactions. When we look at our table, we don't see a carrier particle associated with gravity. Because, as you might have guessed if you regularly watch our videos, gravity is a bit of a tricky force. In fact, whether it's even a force is debatable. I explained this before in our Roberto Carlos video about fictitious forces. I definitely recommend you watch that one too. But in summary, gravity isn't really a force like the others. Because the most accurate theory of gravity we've developed so far, Einstein's general theory of relativity, describes gravity not as a force like Newton imagined, but as a geometric interaction resulting from the curvature of spacetime. But even so, this theory still can't explain the following question. How does a mass interact with the fabric of spacetime? In other words, what exactly does mass do to bend the fabric of spacetime? Well, we don't know that. But in particle physics, we think that this interaction, although such a particle has not yet been discovered, is carried out by another carrier particle called the graviton. But since all the particles in our table have been experimentally observed so far, gravitons are not included in our table for now. Still, there is something we do know. Gravity, like photons, also propagates at the speed of light. So if the sun were to suddenly disappear right now, the Earth would continue to orbit in its elliptical path for 8 minutes and 20 seconds as if the sun were still there. However, according to Newton's theory of gravity, this change should have happened instantly. Indeed, as I mentioned, if you assume the speed of light is infinite, as Newton thought, in general relativity, which is a much more accurate theory of gravity, the theory of relativity essentially turns into standard Newtonian physics. Therefore, relativity can also be considered as a more generalized formulation of Newtonian physics. And the most accurate statement that captures the essence of this magnificent theory comes from the great physicist John Wheeler. Space-time tells matter how to move, and matter tells space-time how to curve. The entire theory of gravity consists of this sentence and the rather complex mathematics that underpin it. Mass and energy in space bend the fabric of space-time, and that mass and energy are then forced to move according to that curved fabric of space-time. Just as a car has to go wherever the road leads, objects in space have to move in the direction in which space-time is curved. But unlike the car and road example, in space-time, it is the mass and energy themselves that determine where space-time will be curved. This mutual interaction is what gives rise to what we perceive as gravity. So, in reality, there isn't an interaction like Newton imagined, as if there were an invisible string between a planet and its satellite, or between you and something else, pulling you along that string. Gravity is nothing more than a universal game of geometry. So now we've learned about the 4 fundamental forces that make up and operate the universe. But a question comes to my mind. Why are there 4 forces and not 1, 3, or 5? Actually, this is, in a way, a philosophical question. Why are there trees, but not completely different living things like Sarchler or Marchlar? There isn't really a realistic answer to this question other than the interplay of a vast physical, chemical, and biological history. There are 4 forces in the universe, because up until now, we've only been able to detect 4 forces. But thanks to those 4 forces, we can explain almost all the experiments and observations we've made so far nearly perfectly. Well, except for a few. For example, the rotation speed of galaxies is much greater than what we would expect from the effects of the 4 fundamental forces. And if galaxies don't have some extra mass that we can't see, then under the known forces, the stars that make up galaxies should have been flung out into the emptiness of space. When we do the calculations, we see that in order to keep galaxies stable as we observe them through our telescopes, this invisible mass must make up 85% of all matter in the universe. It's mind-boggling. This mysterious mass doesn't interact with any known force except gravity. Therefore, we can't observe them with our telescopes and similar measuring instruments that operate based on the other 3 forces. That's why we call it dark matter. Why does such matter exist? Or, as I explained to you before, in the muon G2 experiments conducted by Fermilab, the natural wobbling motion exhibited by muons has an extra amount of wobble that we can't explain with the 4 fundamental forces. Why? Where does that extra wobble come from? Or, when beryllium atoms decay into helium atoms, they make a jump of about 17 mega-electron volts that we can't explain with the 4 known forces. In fact, that's why physicists have named the hypothetical effect causing this jump the X17 boson. What is the reason for this jump? Or, as we discussed earlier, 2 different measurements of the Hubble parameter, which describes the expansion rate of the universe, yield values that are very close to each other, but statistically completely different. Why? What causes this difference? That's why it's wonderful that there are so many unknowns in the universe, because we can propose a single new boson that could solve all of these together. And for this boson to be able to solve all the anomalies I've mentioned, as well as some others I couldn't fit in here, it needs to have very specific properties. Thanks to this, we can know exactly where and how we need to look for it. The problem is, maybe this hypothetical new boson I'm talking about is only related to 2 or 3 of these things, not all of them. Maybe it's not just a 5th force we need to discover, but also a 6th one. We just don't know. So, there are a lot of combinations and a lot of experiments that need to be done. These experiments are still ongoing, and of course, they are generating a lot of debate. There are also a lot of uncertainties in the results. Well, that's how science progresses bit by bit. And also, independent of this fifth force issue, as we just discussed, the fact that we've been able to unify electromagnetism and the weak force gives rise to the hope that maybe, by also unifying this electroweak force with the strong force, we could develop a model called the grand unified theory. According to some theories, these three fundamental forces were truly unified and existed as a single force during the first trillionth of a trillionth of a trillionth of a second after the universe began, a period when not even atoms or quarks could move freely. But later, they separated. Testing the validity of these theories is extremely important, because some versions of the grand unified theory predict that even protons could decay over extremely long timescales. This could fundamentally change what we know about the end of the universe, but unfortunately, there is still no experimental evidence for these yet. However, no matter how hard we try, one interaction always remains outside. Gravity. Because general relativity is a geometric theory, combining it with quantum field theory poses a huge challenge. That's why none of the unified theories developed so far have been able to achieve a complete unification that includes gravity. And this is where the greatest dream of physics comes into play, the theory of everything. In other words, being able to express not just all the forces, but all the particles, all the interactions, everything you can think of, with a single and preferably very concise equation. But this equation still hasn't been written. Maybe the reason is that we still don't know a missing piece. And maybe that piece is a fifth force. And maybe one of the viewers of this video will be the one to discover it. Isn't that possible? It could be. I look forward to seeing you all in the very next video. Goodbye for now.